Okay, so the goal of this video is going to be create a quick tutorial for you that's supplemental to the lectures that we've done. So in case you kind of forgot what we've done or you've missed some of the lectures and need to brush up, I want to make sure that things are clear. So I've created a new project. I've used this project part here just because that's what we use on the basis board, which is what we use when we physically implement things like we did in Lab 7. Okay, so we need to create a new source. I've created this with no sources. So we add this add sources button, and we're going to start out by creating design sources. Clicking next. And then I have no files, so I'm going to create a new file, and I'm going to build a T flip-flop. So what we're going to build up to is a T flip-flop based counter. Okay, so I've created T flip-flop.vhd. We'll come back and make some more in a moment, but we want to start from the basic building blocks. I'm just going to click OK here. You can add stuff there, but I'm going to do it inside of the code. Once you've done the code, created it, it's going to pop up here in the sources window. If you ever lose track of this window, you can always just click on Project Manager and it'll bring back up this sources window, easy to find. In order to open that, we just double click on it and it pops up. Okay, I'm going to make this bigger so it's easier to see, which I can do by floating and then maximizing. Okay, so I'm going to delete all this comment stuff up here because we don't really care about it and it's just going to get in our way. You'll notice that it offers to use this numeric standard. I'm a big fan of using numeric standard in virtually all my designs. The book will occasionally use the unsigned library. Be careful with that one because it's not a real IEEE library and it can lead to some issues down the line. I prefer to use numeric standard. Okay, so a T flip-flop is going to have a couple of ports that come in. So let's go ahead and comment out this port declaration, and we need to start filling it in with ports. So the ports that we need are going to do anything that goes into or out of this device. So what goes into this device? Well, we know we have something called T because that's the input to the T flip-flop. We also know if it's a flip-flop, that means it's clocked. So we're going to have a clock. And those are both going to be inputs of type standard logic. Oops. Okay, so that standard logic, oh my gosh, that autofill drives me nuts and will probably drive you guys nuts too. So I've created those inputs. Notice I ended with that semicolon. We're then going to go ahead and create what our outputs are. Now, we could use just Q, but we'll allow access to Q bar or not Q as well. So those are going to be outputs of type standard logic as well. Okay, so here I've just ended with a parentheses and semicolon because I've got all of my inputs and all of my outputs. We could create a clock enable the same way on this input. You can do the ins on their own lines or same lines like this. I keep it on the same line here just for you guys to keep it clear. So the way I start is I start by deciding what do we need to do. Well, a flip-flop is a clocked process, right? So, or sequential logic. So therefore it needs a clock. If it needs a clock, it needs a process. Inside the process, I'm going to do it on clock or, well, let's see, should I do a reset? Sure. And I'm just going to label this as RST. So sometimes you'll realize that you need a signal or a port later on and go back and fill it in. So I've gone, okay, I want to reset. That is also going to be an input. Okay, so now I've created that. I can go begin on the process, and then I go down and I'll write end process at the very start of this so that I don't forget to clean it up. Okay, so inside of that process, I want to say something like, if reset is equal to 0. Let's make this an active low reset. So we can go back and make that more clear. Reset n indicates it would be an active low, reset n. So if reset n is equal to 0, then we want to set the output to um, 0. So it's going to just initialize to 0. Okay. Else if, oh, there's something that I forgot. So this is going to be an asynchronous reset, meaning that if reset happens, it's going to go to 0 regardless of what the clock is doing. Then we're going to use this nice rising edge command of clock. Then now we're going to do the edge triggering, right? And what does a T flip-flop do on the rising edge of the clock? Well, all it's saying is that if I have asserted T, then I want to change what that output is, right? So we're going to toggle if T. So on the rise of an edge of clock, we're going to do an embedded if statement. If T is equal to 1, then Q is equal to not Q. Okay, but now I've caused, well, I'll come back to the issue that I've just caused. And that if, and this if, and our code is quote unquote complete. Reset is not declared. Oh, because I decided to call it reset n. Okay, so it's not going to like this. It can't read because Q is an output. So now I'm going ahead and go and realize that, all right, I need to do something else. So let's go ahead and go out and create a signal called Q temp that is a standard logic. So I now have a signal Q temp that I can go ahead and use. So instead of this, Q temp is equal to not Q temp. Now that's allowed because Q temp is not an output. Okay, so I still need to do something with this Q bar. Now I'm going to mix combinational and sequential logic. So I built the sequential logic. Let's build a quick and simple combinational logic that just says Q bar is equal to not Q. Well, let's leave it at, not Q temp. And we also need to assign out the output Q, right? Because it's not showing anything. If I double click on it, it'll show me all instances of it. Here I'm resetting Q to 0, but I'm not ever doing anything with the toggles. So let's go and say, let's do above this, Q is equal to Q temp at all times. This is combinational, so this will just happen all the time. So Q and Q bar are both now assigned based on what Q temp is doing. Then here, I probably want to change this to Q temp so that that's what I'm resetting. That could cause me some issues as well. If I tried to declare Q inside this process and outside of it, that would be what we call dual driven, and you might see X's on your simulation. Okay. So now I've created a T flip-flop. Nice, clean, and easy. It should work. Normally at this point, you would go ahead and go test it. I'm going to skip that just because I want to focus more on the building up of devices using multiple. Okay, so let's put this back in the doc and go ahead and do the next step. I need a new design source in order to start stitching these together. I'm going to build up a new source. It's going to be a design source. Next, creating a file. Now, I could call this top like we've discussed, but what this is really going to be is a counter of 4 bits. It's going to be a 4-bit counter. I click OK. I click Finish. I hit OK. I hit Yes. And then it pops up here. Now, here's the thing, is the first one I created is the top. I don't want that to be the top. I want the counter to be the top. So I right click on it, right click, and I say set as top. Now it'll update, a little motion here. I can then open it up. Okay, so let's pop this open and make it big. Again, I'm going to delete all these comments. Those are useful once you're in industry, but for the demo purposes are not very useful. Again, I want to use the standard or numeric standard. And I'm going to need some ports. So this is going to be what we will call the top level entity, meaning these ports are going to be what the test bench is going to see. And actually, let's leave that as commented out for just a minute. We'll come back and decide what we actually need as ports as we go along. This is a fairly normal way to do it, as I did with the last one where I went back and created a signal later. It's fine to go back and create ports and signals after you realize you need them. So what are we going to do with this in order to build a counter? So we have inside of our book, if you go and look at chapter 12, then inside of that, sorry, I'm going to pull it up. I didn't prepare in advance so that I want to be able to give you guys the correct reference so you can go look at figures while I'm doing this. Okay, so here's the book with a T flip-flop counter. So if this one has 3 bits, I'm going to build up 4 bits. You'll notice that the first thing I'm going to say is that the output is going to have Q 0 to N of our bits on the counter as a port, and the input is just going to be this clock enable, which is whether we're counting or not. And then other than that, if the clock happens, and then we have this active low reset. So this is essentially exactly how I've built it up, but I've so far built just individual of these modules. I then just need some AND gates, but that's not particularly difficult to do. And I'm going to show you how to do that, because we're going to use combinational logic to connect sequential logics together. So let's go ahead and start by creating these ports. So the ports that I need are going to be inputs. I need that clock enable. I need clock. And I need reset N. And these, again, are inputs of type standard logic. I'm going to then need the outputs of, well, in this case, it was Q. I'm going to rename this to count. Okay, this is a different type, right? It's an output of standard logic, but it is a vector that goes from, well, I just said it's going to be 4 bits, so it's going 3 down to 0. Okay. Do I need any other outputs? I don't think so. I'm going to have some internal signals, T1, T2, and well, T3 in fact as well, that's going to cascade. Okay, so let's go inside of our architecture. And the first thing we need to do is declare that we have that component, right, that we've just built. So what I do is I'm going to come over here to the T flip-flop, and where it says entity T flip-flop, I'm just going to select that, hit Control-C to copy it, come back here and paste it, and just change the word entity to component and end component. So now this is letting the top level module know that this component exists. I then need to create instances of this. So the way to do that is I'll say T flip-flop 1. That's just the name of the instance. it's going to need to have a name of that. It is a T flip-flop. And it's going to need a port map where we're going to start individually mapping each of these ports to signals. So I'm going to go ahead and do the explicit declaration. You can do an ordered declaration as well, but I won't cover that here because this is a little bit better for beginner students to do, and even has some advantages. You become more advanced in that it makes it more clear. So this is saying the port T needs to be mapped to something. Then the port clock needs to get mapped to something. Reset N needs to get mapped. Q needs to get mapped. And Q bar needs to get mapped. I'm going to add comments at the end of all of these for the moment. And N. All right, so those are all 5. So something that's going to be really useful because I know that I'm going to need 4 of these. Let's 0 index this. So 0, 1, 2, and 3. They all need unique names. These error bars are coming from all over because I haven't said what they are, right? And I'm just going to begin at the very first one. So this is the first flip-flop in this diagram, right? And so it needs to hook up to clock enable. So while the clock enable CE is a port to the outside world, internally I can use that as a signal. So I just call that CE. It is now hooked up and hopefully happy. Okay. Now the clock is going to do the same thing, right? We can just take clock directly, and I probably should have done this before I went and copied and pasted because this is just going to repeat for all of them. Something that you might want to do is change the names of these clocks on the inside. So that's clock, this is clock. It can start getting overloaded. So this is a port name clock plugged into a signal name clock that is tied to the output port clock. Gets confusing, right? But you know, I'm going to leave it on clock because it's universal and I only have one clock. So let's go through and add those, go through and add resets. And then Q is going to start looking at count, right? So Q is going to go to count. So in order to access count, I want count at an index. And I use that by saying count and parentheses. But which index do I want on this first one? Well, if we look at this diagram, the output of Q, the first Q is our Q naught. And that's because this one is going to be changing the most. So that is our least significant bit. So I just say count at 0. Before I do that, I'm going to copy count as this so that I can easily paste. So 0, 1, 2, and 3. So this is where that benefit of going and mapping or renaming T flip-flop 0 to 3 is 0 index is how T flip-flop 3 is now count at 3, right? Those match a little bit better. We also have Q bar. I'm just going to create a signal for that because I don't want to output it, which is going to be basically a count bar, right? Which is going to be a standard logic vector 3 down to 0 as well. Okay, so now I have that count bar, and we're going to say count bar at 0. Update the indexes. Okay, so now these have mapped almost everything together except for these T signals, right? So I need to figure out how to get this T1. So let's create a signal T1. It's going to be standard logic, right? It's just a single bit, so it doesn't need to be anything special. So if you didn't follow all of that, rewatch it, make sure you get it where I'm using these signals essentially from the ports that are created to plug into all of these ports. So CE is plugged into the first T. Clock is poured into all of the clocks. And notice how double clicking on it, highlighting it, shows all of the cases where it's used. And I've wired up the global reset into the port resets. Make sense? And now I've plugged count as an output from Q individually one at a time. But I need to create this signal T1. But what is what is T1? Well, if we look, T1 is Q and clock enable. Well, that's really easy to create in combinational logic right in between these two, right? Where it goes essentially doesn't matter if it's combinational because they all execute in parallel. So we're just saying T1, the signal that I just created up here, is going to be assigned to CE and, well, this Q, right? So I don't want to make the say of saying and Q because it's not. It's the output of the port Q, right? So this port name is Q. What is that output? Well, for us, it was count at 0. So it's CE and count at 0. Try not to confuse the ports and signals because that's really important. Now, this isn't going to like this either, right? Because now I'm back at the problem where count at 0 is now an output and I can't put it on the right side. So let's go back and create a new signal that is count temp, right? We're just going to hold it and it's going to be the same standard logic. Right? I'm just going to copy and paste so I don't have to type it all out. Boom, done, count temp. And now I have to go back and rename all of these counts to count temp. And then I need to just assign count to count temp. Right? Starting to see a pattern of how we start building these up. Okay, so now replace count to count temp and everything is happy. I now have T1 and T1 can go into this next T. And we're just going to repeat that, right? So in our next one, where we have the output Q is going to be T2 is going to be the output of the previous Q ANDed with the previous T1. Okay? So we're going to say T2 gets assigned to not CE, because we've lost that, is now T1 and the output of Q. T1 and the output of this previous Q, which is the count temp. Oh, and I need to create a new signal called T2, which I just can do up here by including it on the same line. I know I'm going to need a T3 as well. Okay, so let's go ahead and create that T3. So the next one, we're going to have the same issue where we're going to take the previous T2 ANDed with the last count temp that we used. Oops, weird spacing. Okay, I'm just adding these returns to keep it nice and legible. Okay, so we've done T1, T2, T3. And you'll notice the last one I don't need to create. So there would be an output, but we can skip that because we can actually just use these. So this is T2, this is T3, right? I've used those names from these signals to connect them together through an AND gate. This is a really important idea to make sure that it all works. But let's do that. And then the last thing we need to make sure we do is that we assign count. Oh, wait, I already did that up here. I assigned count to count temp. Okay, so I hit Control S to make sure that is all saved. And hopefully I have wired everything up correctly. You'll notice the count bar is just floating there doing nothing, and that's okay. So the combinational logic, the connections happen inside this begin. The declarations, letting it know that this component T flip-flop exists, happens between architecture and its begin. So architecture begin. This is how I declare the component, and then I can use that component multiple times, right? So this should all hopefully simulate correctly. So how do we simulate this? Well, oh, and one thing that we can point out at this moment is that inside of sources, I have 4 instances of that T flip-flop. So this is a hierarchical design, right? And it's calling each of them this T flip-flop 4 times. And it shows that it is inside of it, and that this little icon shows that it is the top file. Okay, so let's hit the add button, and we're going to go ahead and generate a simulation source. I'm going to create that file. It's going to be VHDL, and I'm just going to call it, the way that I like to, is counter 4 bits underscore test bench. So it shares the same name and then just underscore TB. It helps me keep track of things that way. So that is created here as the counter 4 bits test bench. Obviously, we want this one to be the test bench to be the top file, not the design source. So here, I'm going to set as top. Now, what you'll notice is that the top for the design and the top for the simulation can and should be different. Okay, so let's go ahead and open up this test bench. Pop this out, make it a little bit bigger. Hopefully this is starting to get familiar and repetitive. Okay, inside of the test bench, you do not need any ports because it's a test bench. Nothing is coming from the outside world, so we're going to have to declare all of the signals that we want. But we need to start by declaring a component that we want. The component that we want, again, I can just use a copy and paste by going to what our design top file is. Here, here for the entity, copying that, bringing it back to our test bench, and renaming entity to component and saying end component. So now our test bench knows this component exists. We're going to need a bunch of signals to make this thing work nice and happy, right? So I'm going to need a signal for each of clock, in, and reset. So I'm just going to copy and paste each of those. Each of those are standard logics. And unlike the other one, with this test bench, I really do need to initialize these values to something. And I'm going to initialize them all just to 0. So you'll notice that means that reset starts as active. That's fine. Similarly, count needs one. Oh, and something that I really like to do that I will show you is I like to, for the signals that I'm using on my test bench, I like to append this underscore TB to the signal names so that it stays nice and easy to keep track of whether it's an internal signal or the top level test bench signals. You'll notice I copied and pasted. It doesn't like it because it has the out. I just delete the out. And there we go. What don't you like? Oh, I forgot a parenthesis. Okay, so I have this component. I need to create an instance of it. Here we call it UUT. It's our unit under test. It is the 4-bit counter. It's going to have a port map. I'm going to show this to you. I don't recommend doing this yet because I don't think you're probably practiced enough, but I can literally just put these in the same order that the ports are ordered. And it will make those connections for me. Now, this is less clear as to what signal is being plugged into which port, which is why it can get confusing. That confusingness means it's going to throw a warning because it's generally not approved of doing that. I want you to know this exists so that if you see it, you can read it. I don't recommend doing this. But let's stick with this for now so that you can see how it works. So I've wired up this UUT into counter 4 bits with these test bench signals. Now we need to do something with this inside of this in this test bench. So we're going to set up the begin and end process so we don't forget the ends exist because that can be problematic. And then we can start making assignments. So we can say things like, wait for 10 nanoseconds. So let's just do nothing for the first 10 nanoseconds. After that, I want to take this. Well, actually, let's start by saying reset N is going to turn off. We're no longer going to be resetting. We're going to wait for 5 nanoseconds. And then we're going to set clock enable to high so that we can start counting. And then wait for 10 nanoseconds. Okay, so you'll notice an issue. What is clock doing right now? So what is clock doing? Unfortunately, it's not doing anything, right? Because if I haven't told it to do anything, it's got initialized to 0, but now it's just kind of sitting there. So we need to make it do something useful. It turns out we can just write something like the following. Let me get where clock test bench is equal to not clock test bench after well, we got to give it a period of time. So let's say 10 nanoseconds. But if we're doing 10 nanoseconds here, this is only going to wait for 1 clock. So maybe I want to wait for 50 well, 10 nanoseconds is probably fine before we lower CS, and then probably 20 nanoseconds. Notice the actual clock period is going to be twice this, because in order to have the clock period, we have to go high and then low and then start making that transition back to high. So it's going to take 20 nanoseconds for 1 clock cycle. So maybe I'll reduce that to 5 nanoseconds. So here we're going to go for 10, wait for 1 clock cycle, wait for 2 clock cycles, enable, and then we're going to wait for a long time. Wait for 100 nanoseconds. Let's pop this back in there. And hopefully I have typed everything correctly, because it's always the worst when you're going through the tutorial and you come back and something's gone astray that I have to correct post simulation. But that's what the simulation is for, is to make sure that everything works out nice. While it waits, I'm going to plug in my laptop so we don't lose power in the middle of this. That would be dreadful. Okay, so let's make this, oh shoot, this thing's in the way. All right. Go ahead and make this big for a moment. Now you'll notice that it has run for not very long. We can run longer simply by coming here and pushing this button, which says go. It's run for another 10 microseconds, which is a really long time. I can change this amount of time. So if I'd only wanted to run for 10 nanoseconds, I could do that. Everything appears to have run reasonably well. Let's go look and see if there are any errors. You can click this button up here, expand, and it will zoom to fit. When you've run so incredibly long, it's not particularly helpful. And so we can zoom back in. So we see the clock is ticking, and we see that the enable goes high, but the count is never changing. So let's go puzzle out, why is count test bench not changing? Is it a test bench issue, or is it a code issue? So count TB is not changing. Clock TB is changing. So this is probably a good time to actually step in a new, it's actually kind of fortunate that this didn't work on the first try. So those are the top level signals. If I want into top low level signals, your command window might start out looking like something like this. You can click on scope and then click on objects. We can then click on the counter 4 bits, and we can look at each of these ones, and we can drag these signals from the counter 4 bit, the internal signals, onto our waveform. That can be very helpful to try and figure out what is happening. So I probably want to look at each of those T's, because those are those clock enables that we have to deal with. And we may want to make sure that, say, the clock internally is getting to where it needs to go. It looks like it is. That's good. It doesn't record all signals by default. So if you need to, we can hit relaunch simulation, and it will update our new internal signals. And we can go back and make this big so we can start debugging. So it looks like neither T1 nor T2 ever change, which is problematic, actually. So let's go look at even deeper inside of our first flip-flop. So it knows T is 1. It has Q as 0. There. Let's step all the way back and look at this T flip-flop and see if maybe I've created an issue in here. If reset is 0, then we reset. Otherwise, if we have the rising edge of clock, then if T is 1, then Q temp flips, and Q temp is switched. Okay, so I feel like that still looks correct, but that doesn't mean it is correct. Let's pull out this first Q and see if it's ever flipping. So this Q is not flipping, and let's make sure we know which one we're pulling from. I'm going to go Q by Q as well, since And I'm just going to snag the last one, Qtemp, and the first one's Qtemp. So now I have a ton of signals, and hopefully one of these is changing, because if they're not, then something really weird is going on. Qtemp is zeros. So none of my Qs are changing, which is obviously problematic. So we're going to have to puzzle out why that is. Oh my goodness. So I realized what it is my reset. I never set it back high. I set clock enable high, but I've never set reset back to high. So let's go fix that in the test bench. So here's the issue. We've done this waiting, and let's set reset back to high. And now let's try this all again. Oh shoot, why is this in the way? It really needs to hide. Go ahead and rerun the simulation. Sorry, I don't know if you guys can see it on the Zoom share, but my Zoom panel has decided to get in the way, and it's not default hiding, which is strange. And I'm going to run this for an extra 1,000 nanoseconds. Just make sure it runs nice and long. Pop this big, pop this out. Zoom to fit. And now it looks like we might actually be counting something. 0, 1, 2, 2, 3, 4, 0, 1, 2, 3, 4. Well, oh, this is actually really funny. So the reason it's not counting longer than that is I'm not waiting long enough. So you'll notice that it's going 1, 2, 3, 4, reset, because my test bench is not set up to wait long enough at the end there. Let's just wait for a really long time at the end of this. And then once again, we can rerun that simulation. There we go. That looks much better. You'll notice that this is in hexadecimal, which is fine. So we're going 1 A B C D E F, and then we're hitting 0 again. Right, we're rolling over, which will become more apparent, I think, to you if I change the radix. So I can right click on get count, and its default is hex, but I can change this to unsigned decimal, so that now I just have numbers that go up to 0 to 15. Think about it. Why does it stop at 15? Well, it's a 4-bit counter, and so once that all rolls over, we're back to 0, and we're just rolling around. But anyways, you got to see some of the counting. You look at all these internal waveforms of how they're counting. I think that covers basically everything you need to know as far as using VHDL. like an actual implementation. So I hope this has helped everybody, and let me know how this goes.